Morning, students. Yesterday, we started a new chapter, current electricity, and we discussed when current comes, electric current flow in a conductor. The first point is, it should be a conductor in general. There is a free availability of charge carriers. In case of metals, electrons are the charge carriers. When these charges move, due to the movement of charges, current comes. If that movement is in a short duration of time and ceases after, that current due to just movement of charges for a short duration, transient current. If the same free charge carriers, those are electrons, they move continuously, that gives a continuous current that generally we call it as electric current in the circuit, in the material. Well, for the continuous flow of charges, what we have to do? We must apply an electric field. For applying an electric field, what we are doing? See, this is a conductor, one conductor. To have a continuous flow of charges, an electric field is required. For that, what we are doing, we are connecting these ends of the conductor to a source, which is cell. What cell does? It creates a potential difference between these 2 points. This end comes to positive potential, this end negative potential develops. We know positive charge flows from positive potential side to the negative potential side. So there is a potential difference between these 2 ends. Once potential difference comes, an electric field is set up between the ends. That electric field is E, let us say. When I apply an electric field, the free electrons inside of this conductor, what happens? All those electrons they move from negative side to positive side, and again they go in and comes to the battery. Battery again drives them to go to the circuit. So there is a continuous flow of electrons in the circuit. And one more important point I said, conventional current direction is opposite to the direction of flow of electrons. So whenever electrons are moving in this direction, what is the direction of current? This is the direction of current. Yesterday, I stressed on that point. Direction of the current is the direction of the flow of positive charges opposite to the direction of flow of electrons, right? Well, this is what we discussed yesterday. Now, battery connected, potential difference is developed between the ends. Due to that potential difference, all these electrons are moving from negative side to from negative end to the positive end of the conductor, and this flow is continuous, right? Well, if I take any cross-sectional area in this conductor, see what this dotted line represents. This is a cross-sectional area. This is some cross-sectional area I am choosing. This is cross-sectional area I am choosing. This is cross-sectional area I am choosing. Right? If Q amount of charge crossing through any cross-sectional area in time t. If you see this diagram, 4 electrons are crossing. How much charge is crossing there? 4 into E. Here 4, 4, 4. So through any cross-sectional area, the amount of charge crossing is constant, that is Q in this particular case. So Q is the amount of charge crossing through any cross-sectional area in certain time t. Then the current flowing through this conductor is Q by T. Charge by time. From this we can define the current as rate of flow of charge through any cross-sectional area of a conductor, through any cross-sectional area of a conductor. That is the definition of electric current, right? Q is the amount of charge crossing through any cross-sectional area in time t. Then electric current is Q by T, right? Next. Current. Sometimes we find the word average current. Generally, when the charge flow is steady, 2s, charge flow is steady. Charge flow is steady means what? This example. 4, next 4, next 4. Through any cross-sectional area in a particular interval of time, constant charge is crossing. Here, Q is the amount of charge crossing in particular interval of time t. Whenever you see that same charge in the same interval of time crosses, then average you can take it as Q by T. Simple. If charge flow is not steady, charge flow is unsteady. Sometimes 4 charges, 4 electrons, after that 8 electrons, after that again it is decreased to 3, like the charge flow through the cross-sectional area is varying with time. Charge flow is not steady in the sense charge is a function of time. Charge crossing that area as a function of time. Then I average delta Q by delta T. Delta Q by delta T. Remember, I'll tell you an example, then you come to understand. When it is, charge flow is not steady. If charge flow is steady, whenever you calculate, it comes as Q. Between any 2 seconds, after 2, after like anywhere, if you calculate, this ratio is constant. Steady charge in particular time interval. But here, with time, Q is varying. In that case, delta Q by delta T. That is average current, we call it as. From these two, it is clear that when the flow is steady, average current is considered as current flowing through the conductor, right? Another, see, what is that important point? In a steady flow, charge, steady flow of charge, current through a conductor is equal to average current. Current through a conductor is equal to average current. But the flow is non-steady. You can't say that. It differs, right? Next. Come on, note down. Well, next. Instantaneous current. Instantaneous current. That name itself tells you current is flowing continuously in a conductor, whether it is steady or non-steady, at a particular instant of time, at a fraction of time, at that particular instant of time. If you calculate the current flow, that you call it as instantaneous current. Current at a particular instant of time, right? I instantaneous, we call it as I instantaneous. Mathematically, what it is? Limit delta Q by delta T, where delta T tends to 0. Delta T tends to 0 means very less interval of time. Very less interval of time. if you calculate the average current, which is equal to instantaneous current, limited to very small interval of time, that is the meaning, delta Q by delta. We write it like this. I instantaneous, limit delta Q by delta T. For a small change, we write like this, dQ by dt. This is instantaneous. Right? One more. In steady flow. In steady flow. Instantaneous is equal to I average. Steady flow at any interval of time, at any fraction of time, at any instant of time, if you calculate the current, if the flow is steady, it is Q by D, Q by D, Q by D only. Whenever you calculate Q by T, dQ by dt, which is equal to dQ by dt, instantaneous. So whenever the flow is steady, then I instantaneous is equal to I average. Remember it. If it is non-steady, simply telling you at a particular instant of time, more charge is crossing, current comes more. At a particular instant of time, less charge is crossing the area, less charge will come, less current will come. So I instantaneous is not equal to I average when it is in a non-steady flow. If the flow is steady, I instantaneous is I average. You can take it. Okay? Remember this. Well, what is the unit of current? SI unit of current. The simplest formula of current is I equal to Q by D, whether it is dQ by dt, Q by D, delta Q by delta T, whatever it may be, Q by T. So what is the unit? For Q, Coulomb. For time, second. Coulomb per second. Coulomb per second. Right? That is in symbol, Coulomb per second. But we won't use this Coulomb per second. We use a name called ampere. This Coulomb per second called as ampere, name of the scientist. After his name, it is given. Ampere, right? So what is the unit of SI unit of current if you ask? Ampere. 1 ampere, ampere represented with capital A. So 1 ampere, 1 coulomb by 1 second. 1 coulomb by 1 second, right? How to define ampere? Definition of ampere. One coulomb per 1 second. 1 coulomb of charge crossing any cross-sectional area in 1 second in a conductor, the current flowing through that conductor is said to be 1 ampere. How much charge? 1 coulomb of charge crossing any cross-sectional area of a conductor, cross-sectional area in 1 second in a conductor, then current through that conductor current through that conductor said to be 1 ampere. Said to be 1 ampere. Right? PU point important. Formula and definition. That is the unit. One more. Clear? Come on. Next. Unit okay, definition okay. Current, is it a vector or a scalar? Current is, I is a fundamental quantity. We have 7 basic fundamental quantities. Among them, current is one fundamental quantity, like length, mass, time. It's 7 fundamental quantities. You studied in first year. When we come to current part, I is the fundamental quantity, fundamental physical quantity. And current I is a scalar. Very important. Current is a scalar. If you ask, is it a vector or a scalar? It is a scalar. But one doubt will come. A small doubt will come. When I connect this conductor to the cell battery, to the battery, current is flowing. Electrons are flowing in this direction. Then current direction in this case, current direction is always from positive to negative, opposite to the direction of flow of electrons, from positive terminal of the battery to the negative terminal of the battery. Again and again I am telling you, you have to remember. From the positive terminal of the battery to the negative terminal of the battery, from the positive potential side to negative potential side, current direction, opposite to the direction of flow of electrons. Clear? So if you observe here, current has magnitude, some value. From the calculation we get I q by t. If you know q, if you know t, you get I value. Magnitude it has. And from this diagram it is clear that current has a particular direction. As current has magnitude as well as direction, even though we are not considering it as a vector, it is a scalar. Why? One of the important question, a regularly asking question in board exams. Even though current has both magnitude and direction, current has both magnitude and direction, it is not considered as a vector. Why? It is not considered as a vector. What is the reason? Explain with an example they ask. See here. This is one conductor. This is another conductor. And this is another conductor. These two are connected here, and this is the line. Another wire is connected. 3. In this, some 3 amperes of current is coming, let us say I1. In this, some 2 amperes of current is coming. These two conductors are making certain angle theta. Then what is the net resultant current flowing through this? Practically, if you measure, the current flowing through this conductor is simply the sum of 5. This one and this one. 5 means I is simply I1 plus I2. If it is a vector, if you consider this angle, you have to consider that angle. This formula you have to use. I is equal to, if it is a vector, I1 square plus I2 square plus 2 I1 I2 cos theta, that you have to use. When we use this formula, you get a different value, right? Whether these two are like this with an angle 60, let an example, cos 60. Calculate, you won't get phi, some other value you get it, right? But see, you check out just by calculation. 3 square 9, 2 square 4, 2 cos 60 1 by 2, 2 get cancelled, plus 6. 19, right? But this is phi. It is not this value. So means it is not following vector addition. Even though it has both magnitude and direction, it is not following the principle of vector addition. What is the conclusion? Current does not follow the principle of vector addition. So it is a scalar. That's it. Give an example. This is the example. Two currents, 3 and 2 amperes are flowing through two conductors. When it is connected to another conductor, the current through it is phi. It is not 90, right? If it is root 90, we can say that it is following vector addition. But we got phi. It is not following vector addition. Means it is not showing the complete property of a vector. It is not showing vector, not following the vector addition property. So it is a scalar, right? Write down. Next. different cases we see. If current flowing through a conductor I is changing with time. Changing with time means as a function of time. Then what they ask, what is the charge flowing in a particular interval of time? If current flowing through a conductor is changing with time, that means function of time. Question is what? What is Q charge flowing through the cross section in a time interval T1 to T2. In a particular time interval T1 seconds to T2 seconds. How much? If I is a function of time, right? Let us see. We know I is dq by dt. We know this. I is equal to dq by dt in a small interval of time. You can write dq is equal to I dt. dq is equal to I dt. You are asked what is q between the time intervals t1 and t2. You want q, integrate dq, right? Between the time intervals t1 and t2. So I dt between t1 and t2, right? That's it. We'll see one example. Given that current is some 2t square plus 3t. When we see this I is a function of time given in terms of time. Whenever given in this form, it clearly tells us that I is a function of time. It is not a steady current, changing with time, right? Given like this. And between the time intervals, t1 is equal to 0 to t1 is equal to 2 seconds. Between this time interval, what is the charge flowing through any cross section of the conductor, through a conductor or through any cross section of the conductor? What is the charge flowing? They ask. Simply, what is the formula? See here. Q integral t1 to t2 I dt, right? And apply. Integral of t1 0 t2 2 seconds I 2t square plus 3t. Integrate it to integration of t square t cube by 3, right? 3 integration of t square by 2. Apply the limits 0 to 2. Then you apply the limit to upper limit to, in place of t, take 2 cube minus 0 by 3. Here 3 by 2 square, 2 square, 0. Then simplify this. 2 cube 8, 8 to the 16 by 3. Here 4, 4 3 the 12 by 2. You simplify this, you will get the charge. That's it. Right? Come on, write down. Next. If n number charges, n number of particles, each of charge q, each of charge q passing through cross-sectional area of a conductor in time t, what is the current? What is the current? This diagram tells you, let same thing, 1 2 3 4, 4 is n is equal to 4 here in this particular example. Q is what? E, charge of the electron. Q is equal to E, right? Crossing through any cross-sectional area of the conductor, what is the current here? Total number of charges 4. Each charge E. What is the total charge crossing? Q is equal to NQ. Can I write? Each charge is Q. Then total charge N into Q. Then I is Q by T. Means NQ by T. In this particular case, this is NE by T. Let to cross any cross-sectional area, let it takes t is equal to 2 seconds. You can calculate here simply. In this particular case, n is 4, e is 1.6 into 10 to the power of minus 19 by 2. Simple. Then 3.2 into 10 to the power of minus 19 ampere. Like. So what is the final formula? I is equal to Q by T, where Q is number of charges into number of particles, charge of each particle, NQ by T. This is the example. In this particular example, 4 are crossing. I took n is equal to 4. What is the particle? Electron. Electron is the particle. So each charge is E. So total charge NQ. In what time? I gave 2 seconds. Then what is the current? NQ by T. That's it. That is the fact. Next. Well, another important application. This is a discharge tube. Discharge tube. Generally evacuated glass tube. Discharge tube. The tube in which pressure is maintained at very low value. Connected to a high tension battery. This is positive plate. This is negative plate. That is discharge. Let here N1 number of protons. How many number? N1 number positive charges. See, I am representing with this color protons. And how many number? N1 number of protons and N2 number of electrons. Electrons move from this plate to this plate. I am representing with different color. Electrons. Different color I use. E plus అనకూడదు. Electrons. N2 number of electrons. How N1 number of protons are moving from this is left side, this is right side. N1 number of protons moving from left to right. In the same way, N2 number of electrons moving from right to left. Right to left in time t. From left to right, n number of protons are moving in time t. In the same time, from right to left, n2 number of electrons are moving. Here the question is, what is the total current due to the movement of both electrons and protons? What is the net current? I net current means current is due to protons, current due to electrons. Right? How many protons are there? N1. So N1 number of protons. Each proton charge we know. E charge of each proton. What is the time? T. Finish. And N2 number of electrons. What is number N2 for electrons? What is the charge of each electron? E. How much time? T. Right? But the confusion comes for us. What we have to take it here? Is it plus or minus? That is the confusion when this question is asked. Let us see. Current direction is always in the direction of the positive charge. Proton is positive. So what is the direction of current due to protons? I proton direction. I due to proton. They are moving from left to right. Left to right. Then what is the direction of current due to electron? Here is the concept. Current due to flow of electrons is always opposite to the direction of flow of electrons, right? Current produced by the flow of electrons is always opposite to the direction of flow of electrons, because electron is a negative charge. Opposite, it is in the direction of the positive charge. In previous cases I told you. So current due to electron is also from left to right. You understand this point? This is very important. Because electrons are moving in this direction. So current due to electron, opposite to that. Current due to proton, positive to negative. See both how they are in the same direction. So what we have to take it here? Plus only. Well, as both are in the same direction, they add up. Plus. So what is the answer? N1 plus N2 E by T. What is the direction? Left to right. This is the question asked in previous entrance, along with the direction. Right? One of the important conceptual problem. It is there in exercise, and one problem is there in third level. You try to do those problems. Okay? Next class, that is coming next class, maybe on Monday. Tomorrow, I hope Independence Day. There may be no class. We'll inform you. Next Sunday and Monday's class will continue.